afternoon, everyone. It's a pleasure to welcome Dr. Ming Liu from the Institute of Microelectronics, the Chinese Academy of Sciences in Beijing, People's Republic of China, as a Waterloo Institute for Nanotechnology seminar speaker today. Dr. Liu received her BS and MSc degrees in semiconductor physics and devices from Hefei University of Technology in 1985 and 1988, respectively. For PhD, she received her PhD in material science from Beihang University in 1998. Her current research interests are in micro and nano fabrication, memory devices and integration, nanoelectronics and molecular electronics. Dr. Liu is also currently the director of the Laboratory of Nanofabrication and Novel Device Integrated Architecture. That's called IMICAS. Dr. Liu is a very accomplished scientist who holds more than 30 Chinese patents, with more filed and pending, and has published 3 books in collaboration with others, more than 180 journal papers, and more than 50 papers, including 18 keynote or invited papers in international and national conference proceedings. Dr. Liu won the Elite Young Scientist Award from the National Science Foundation of China, which is, I think, the highest honor bestowed on a young scientist in China, in 2008. She received the National S&T Progress Award at the 2nd level in 2009, and the National Invention Award, the 2nd level in 2007 and 2005, as well as a number of other awards from the Beijing government and the Ministry of Education. Please welcome Professor Ming Liu.
So good afternoon, everyone. Thanks, Professor Cass's invitation, also introduction to me. It's my great honor to have chance come here with Waterloo University. Also have chance to give a presentation to introduce our institute and some of our research projects. I believe this is the beginning, as from after this the mutual visiting, which we can find some common interest in to further found some common interest into further collaboration. So today I just to give this presentation. The name is RRAM, is a resistant switch memory. It's a new emerging non-volatile memory technology. So here is the outline of my presentation. First, I spend several minutes to introduce our institute. Then I will give an overview of what's the non-volatile memory, what's the challenge of this technology. Then I introduce the RRAM's opportunity and the challenge. So in the first part, I introduce some work, all groups work in this area. So finally, it's a simple summary. So here, just see this is a bird view of the around our institute area. So the location of our institute is here. So here is a very famous bird nest for the 2008 Olympic Stadium. So this location is a very nice location, our institute in Beijing. Just 10 minutes close distance from here to this bird nest. So also around this area, a lot of garden. I think everybody know Beijing is a large population, around 20 million population in Beijing. So it's a very noisy city. But around this area, a lot of garden, so the population density is comparatively very low, but cannot compare with here. So we stay in Beijing. We think it's a nice area. My apartment also located just here, very close to our institute. So only 8 minutes walk distance. So in Beijing, it's a very nice adventure to live in the big cities. So here just show some of the enlarged pictures. Here's our institute. This is the clean room building here. Here is our office building. So it's a campus of an institute. It's compared to this campus, it's a very small campus for this institute. So actually, I know maybe a few people know Chinese Academy of Science. It's a very special organization in China. I think in the other countries know this kind of the organization. It's just dedicated for research. They are not undergraduate program. But they have the graduate students, both for the master and PhD degree. We have right to assign the master and PhD degree to a student. It's not unnecessary to collaborate with the university. Or just the Chinese Academy have this right to give the master and PhD degree. Also, there are high reputation. If you get the master and PhD degree from Chinese Academy of Science, in mainland China, even can equal you get this degree from Peking University, like the Tsinghua University. It's a high reputation for the research. So at this stage, there are around 100. Exact number I cannot remember, but more than 100 institutes around China. But in just more than 40 institutes located in Beijing. But the Chinese Academy of Science, they are located different area, even in the Xinjiang, in the Lanzhou, the northwest area also have their institute. So for our institute, it's just focused on the microelectronics. There are only institute in Chinese Academy of Science dedicated for this area research. So actually now, I think maybe this is the upgrade data. Where our employees is larger than the 1,000. So every year we are include some new employees. So also we have actually now we have the graduate students more than 500. So also some postdoctoral fellowship. So this student beginning the history just can trace back to the 1958. That time they just focus on the silicon-based technology because in that area China didn't open the door to the outside. Was everything should be made by themselves. So for some useful the silicon-based transistor and IC should developed by themselves. So this institute just focus on this area. So they have a very good reputation for this area. A lot of number one is from this institute. But this institute also experienced very tough area. Actually, it's similar with the Chinese economy developing. Because in the early 1980s, China opened the door to the outside world. So for the IC industry, it's the free market. You can buy. So that time, for this institute, is very tough time. You don't know what you should do. If you compete to the outside market, you know this ability. But if you do some advanced research, at that time you have no so strong facility can support your very advanced research. So also they changed a lot. In that time, we changed to the microelectronics research center. That time we like to learn experience from the Japan and Korea. We know in this period, microelectronic fabrication is transferred from America to the Asia, especially for Japan and Korea. They get a huge success for the fabrication for this area. So China likes to learn the experience from the Japan and Korea. But this area is a failure for the finally proved. So in 2003, we changed to the institute again because most the unit in Chinese Academy of Science is the institute, not the center. So actually now, today is a very bright time for this institute because the government gave a lot of support for this area. We actually know from the last 5 years plan, you know, for China, every 5 years have a plan for the government. They pronounced 16 big projects. The number 1, number 2, number 3 is just related with the microelectronics. Number 1 is related with the IC design and the circuit this area. Number 2 is the process technology and the equipment. Number 3 is for the communication related circuit. So they give a big support for this area. So our institute also benefit for this government support. So now we are In the past several years, this institute booming very greatly. So you can see, actually now we have the 11 department. The part department, half department is involved in the IC design. Also, the other half is involved in the process technology. You can see for the process technology, we even have some of the silicon-based technology. For our department is mainly based on silicon-based technology. Also, for this integrated circuit advanced process, this also is a silicon-based, especially for logic device. There are also for the 3-5 compound semiconductor-based technology. Even we have the one department involved with the advanced equipment technology. This is roughly, so our research activity can cover every aspect of the microelectronics field. So here just to show our department. I'm the responsible for this department. We have very strong nanofabrication facilities. So we have 4 e-beam systems, 2 for mask making, 2 for direct writing. So in this, we are mask making shop. Also have electric testing, the optic testing, physical property characterization. So this facility supports the different research directions for memory. Memory with involve a different kind of memory. RRAM just for the advanced fundamental research. We also do some collaboration with industrial area, do some commercial memory. The most focus on design, also for the modified process technology with collaborate with the foundry. So also we do some of the molecular electronics with also carbon-based electronics device. So as we have special group just focus on diffraction optical elements, just focus on the special wavelengths for the X-ray wavelengths. This is very special. There are special requirements, also have special application. Also, we have a group for the gas sensors. So our fundamental is still focused on nanofabrication. So before we are research background, most of this department's research background is from nanofabrication. So we still focus on this area. So here just show some of the equipment. This is for mask making. This is a very old machine, even installed in 1980s, the middle of 1980s, but today is still working. We can provide the commercial mask for in the mainland China, even abroad. Every year we can earn, from this market, we can earn 5 million Chinese yuan. So this is a big support for us. So also the e-beam system, this is the e-beam system. It's a very old e-beam system, but this is compared to the new e-beam system for mask making, is donated by the Applied Material. So there are 2 e-beam systems for direct writing. Both come from the Jewel company. One is 15 kilowatt, another is 100 kilowatt. So this is the 2 direct writing e-beam system. For this is the new e-beam system. They can down to the spool size can to 2 nanometer. The maximum resolution can reach to the 80 nanometer. So based on this facility, we have very strong capabilities for nanofabrication. Also with thin film deposition, we have the SPAT system, ALD system, also e-beam evaporation, also the high temperature PCVD systems. For the process, we have Elena, also etching. This etching is fabricated by our institute. Also some of the ferro, also RTP. So we already ordered some new etching system and a new SPAT, even the new LED system will install early next year. So some maturity system, for this we are very strong. We almost all the electron maturity system is already finished. So we have some testing system, but for the physical characteristic system not so strong. Usually we are collaborating with the Nano Center, also located in Beijing, also Physical Institute, Chemistry Institute. They have strong these facilities. This is just a very simple introduce our institute, especially our department. So then the third part was the non-volatile memory, because I think here the different background. So memory is very familiar to everyone. I think everyone, even you don't know what's the structure, what's the principle of memory, but you use memory every day for your camera, for your USB, even for your computer, everywhere. So for memory, roughly speaking, three different kind of memory. Is working memory, usually for the DRAM, SRAM, used for is a very high speed. But this kind of memory usually is volatile memory. That means if you remove the outside electrode, the stored data also disappeared. That means the volatile memory. There are two another different kind of another memory is the embedded memory, also standalone memory. These two kind of memory usually is a volatile memory, non-volatile memory. That means even you remove the outside the external electric field, the data still kept. That's a non-volatile memory. For memory is very important. There are three reasons. One is you can, from market value, you can the year by year the memory market value increase largely. For the second reason is you see even for the SoC technologies will become more and more important. We can see for SoC, the logic only occupied a very small size. We see today's CPU, only 25% is a logic area. Most another area is for the memory. So so memory technology is a great influence for the feature size, the size, even the silicon size. Also for the third part, you know, every new technology is beginning from memory, not from the CPU. That's because for memory, there are similar structures, easy to test the new technology. So memory is so important because these reasons. But today we just focus on non-volatile memory. We can see what's the structure of non-volatile memory. Just here, this structure is very familiar with everyone because the CMOS technology is similar like this. This is a source string and the gate. The logic device is like this structure. But for memory, this just have a floating gate between the gate and the channel. This floating gate used for to store the data. Even when you like to store data in the floating gate, you get the voltage from gate to substrate. Then you can inject the carrier in the channel into this gate. You can design this with value 1. When you use reversed voltage, you can reject this carrier in the floating gate into the channel again. That means they remove this charge. So they can design this for the value 0 that can store it and remove the data. So this structure is very gets a huge successful in the market. We know this structure was invented in 1967 I think it's from Bayer Laboratory. But it gets the beginning to the really application is in the middle of the 1980s. That's because this is a single cell structure. But how to get the efficient RRAM can get real application. This technology is invented by the Toshiba Technology Institute. So then they get a huge successful. So even today, we all know the Samsung is the #1 for the non-volatile memory, but they still pay the IP the charge for the Toshiba. But this structure also faces big challenges when the further scaling down. We know that for the CMOS technology, the bigger advantage they can scaling down from one generation to next generation. They didn't change the structures, just shrinking their feature size. But for the memory device, even meet a larger challenge than the logic device. The reason is because the big challenge is from the gate oxides. We can say from the gate oxides for the logic device, from the one generation to next generation, their gate oxides also simultaneously reduced with the gate lines. That's the same. But for the memory device, we can say for different technology generation, their feature size reduced from one generation to next generation. But their gate oxides cannot shrink simultaneously. That's because for this structure, we can say if this gate oxides become thinner, they cause some of the tunneling between the floating gate to this channel that will lost the stored data. Because we need usually for commercial requirements, we need the data can store almost 10 years. This is the commercial requirements. So for these requirements, we cannot reduce the gate oxides simultaneous with the feature size. That's a big challenge for this technology. So today, most predictions think for the down to the 20 nanometer flash memory where cannot work again. So we can say if who can be the candidate for the sub 20 nanometer memory, we can say we should meet some benchmark, usually with low power, so for different application. So here just show both the NAND and NOR is the flash memory. Also we can see some new memory like the Ferro, the RRAM, DRAM, STT is a kind of MRAM. Also RRAM, even the NAMS-based memory. We can see if you compete with today's floating gate memory, we should meet these requirements. Firstly, we should the capability can get to the multiple level. That means one cell can stay not 1 bit, the several bit. Also the cost is comparatively low. Also the reliability can compete with the flash memory. Even the density are larger to today's flash memory. Also the bigger problem for today's flash memory is the speed. The speed is should larger than today's commercial flash memory. That's the basic requirement for the next generation memories candidates. Sorry. So another requirement is say from today's technology, the 3D is more important because if you further the shrinking the feature size is so tough. But another choice, you can stick these structures. We use 3D technology. Can you keep the feature size the same, but still can increase the density. So for the future's memory application, you should first you can compete with today's flash memory. Also the second, you are suitable for the 3D application. So for the RTS, they think the two technologies are very important. In 2009, I think RRAM is one of strong candidates for the future non-volatile memory. But in last year, they are also modified their STT MRAM is RRAM also. Think is a strong candidate for the future. Even not only for the non-volatile memory, even they have capability for the future universal memory. That means they even can work for the working memory. So let's today why they have so many interest into research in new memories because of today's occupied markets, the flash memory face some big challenges. So we can see what's RRAM. So basically, RRAM is a very simple MIM structures. Is very simple, but this structure there are some requirements for this structure. They can transfer from two very stable states. So when the electrical pulse, extra electric pulse was except for these two points, they can change it from one state to another state. Even they remove this extra electrical pulse, this state is kept. Can use for non-volatile memory. So until now, there are a lot of material was found this phenomena. So you can a lot of different material. They have this function can meet these requirements. We can say the TMO material, even the metal doped polyescape material. There are also a lot of different materials. They also demonstrate a lot of advantage. You can see very simple structures, just MMT structures. Also very good compatible with CMOS process. If you choose some very simple transition metal oxide, they can choose the compatible process with CMOS technology. Also, they can demonstrate very good scalability for the future application. They can down to the 8 nanometers for publication. Also, with a larger ratio, on-off ratio, let me for the single cell, they can ability to demonstrate the multiple level storage. Also, they explore very fast speed. We see for the flash memory, usually the speed is micro to the minus second. But for this, we can demonstrate even a nanosecond. So you can compatible with DRAM. Also, good endurance. That means the data can cycling several times. This is a commercial value for 10 to 6. Also, good retention. That means they can store the data more than 10 years. But for real applications, you should get a trade-off from the different requirements. We can say for this, we need pore density, or throughput, read throughput, write throughput, also endurance, also the random access the throughput. We should trade-off between these different requirements. We can see for different applications, there are different requirements. For we can see this color is for the embedded memory, the blue color is for the working memory, the red one is for the standalone memory. We can see for the RRAM, we mostly can use for either for the embedded memory or for the standalone memory. Even for the working memory, there are still some compatible. So we can see for example, for the future embedded applications, very easy for RRAM. If you use the back-end technology, we just finish the most process, then in the contactor, the interconnect, this level, we just integrate RRAM in the interconnect, the back-end technology. We can see this couple interconnect, just use this couple with oxide, this couple to couple oxide can become the RRAM cells. This is very easy to integrate with this back-end technology, also very low cost. So for embedded application is very easy. You can very compatible with the logic device. So also for the 3D application, they are very strong the computation for this technology. We can see because RRAM is the MIM structures, they are easy to stable several different cells together. So can get a very small the feature size. So that means RRAM can meet the requirement for the future memory application. So, but there are still a lot of challenges for this technology for real application. First, we can see so many material demonstrate they have RRAM phenomena, but this is also is advantage, also the big challenge. So usually for the CMOS technology, they don't like so many material. They like some materials because the contamination. So if we cannot fix one material, it is cannot get the real application. This is one challenge. Another is we can see they still have a larger variation for their parameters. You can see for the low resistance states, it's more unified, but for the high resistance states, they are so large distribution. This is not good for the real application. So now is scaling down issues. Even today, we demonstrated the 9 nanometers device, but for the if you use for the larger integrated, they are still not this kind of demonstrated that this is only a single device. So how about the integrated, the larger density circuit is still a question. So also for reliability problem, because there are so many material, there are no good understand for the mechanism for this switch. So there are also no model to detail describe the reliability problems. Also, the most big challenge of today is still unclear the mechanism. Until now, there are a lot of material, also different materials, they are based on different the mechanism. But today, the most the commercial, common mechanism is based on the metal on oxygen vacancy based the filament forming and rupture process is responsible for the switch process. So also for the future integration, we show the structure is just a resistor. If you for the real application, you should have a selector transistor on a diode. But if you use the transistor as a selector device, finally this memory device, their feature size is dependent on the transistor, not this R size. So the bigger problem is if you can use a diode, it can greatly integrate the density. But for that, there are some requirements. If you use a diode for the selector, so you should balance from the, usually for RRAM, we should reduce the reset process for the low power application. But for the select transistor, usually we hope the current density is very high in, for the selector. So this is the challenge for this technology. So based on this area, we also do some research work on the RRAM. We just simply choose this material. Actually, we try different material. We also try hafnium oxides. But today, I just introduce all the work is based on this zirconium oxides-based material. Because this material is very simple material, is compatible with CMOS technology. Also, this one kind of the high-K material can use for the logic device. So first, I just introduced some work on this RRAM. Then we try to understand this kind of material memories, their switching mechanism. Also, based on this understanding, we know there are some variation. What's the cause of the variation for this device, the parameter? So we try to use some way to control the filament forming process. Then also we do some work for the future 3D integration. And finally, we demo 1K the test chip for this RRAM. So for the fabrication, the device is very simple. We just use the full commercial compatible with CMOS technology the process. This is the device structures. So this is the performance of the device. We can see this device is no polar characteristic. That means that even you use the positive and negative electric field can trigger the set go and reset process. We also see there are very large the ratio between high resistance states and low resistance states. That means they have the potential for the multiple level application. Also, very fast speed, we can reach the 15 nanosecond for the set process, also 100 nanosecond for the reset process. Also demonstrate a long rotation time. So this is this basic performance for this device. We also choose a different doping. We can see this. Sorry. So this device is doped by the copper. So this then we use the tantalum as a doping. We can see compare with the undoped device with the doping device. After doping, their either set and reset the parameter was narrowed a lot larger. That means greatly improve the performance. Also, we can see use a different doping also can change the priority of this kind of device. We try a lot of different way for the doping. Actually, now we collaborate with the implantation company to detail understand the doping, the influence to this material. Because not only for the RRAM application, they also for the fully understand the different doping elements, the doping dose, even the different doping weights, the influence for this material. For the detail understand this influence can really understand this material is really useful for even for the logical device. So the second part we like to know, even first we just fabricate the device, then we like to understand what's the switch mechanism. So the first we also use the electron measurement. We can say, say from this measurement we can deduce some of their mechanism. First, say their current slope is close to 1 in the on state. That means the on state is they behave like a metal. But another is the resistance of on state is no relationship with the cell size. There's a different cell size is the same. That's easy to answer if you think in the on state is the metal conduct filament was formed. The resistance just depend on this filament, so the cell size is not so big influence from this. Also, we can see the reset current is related with the set process. We show that this device usually when the measurement use the complex current in the set process, that involve the damage of the device. If you use a small complex current, then usually can form the very thin filament. That means in the reset process, you use very small current can broken this filament. So based on this electron measurement, we can deduce this switch process is responsible for the filament, the forming and rupture process. But you cannot to understand what's the nature of this filament. So next step, we do some temperature dependence measurements. We can say for the on state, that's one the low resistance states. You can say that this is get the thermal coefficients is a different device get almost similar values. We compare to the copper nanowire, they are similar value with the copper nanowire. So from this experiment result, we can see in the on state, this filament is consistent with the copper. So based on this experiment, we propose this the forming process. Just the filament, the copper filament was formed between the top and bottom electrode. For the reset process, this filament was broken. So then to the off state, this on state. But this just deduced for the really understand, we should take the TEM picture to observe this process. So this is a very challenging job because if you do some TEM experiment, you can understand it. This is a device, it is very difficult how to make the samples. But this sample device just fabricated on the tungsten tip. So it's not so easy to get successful for this samples preparation. But actually, for this, after 1.5 years, a lot of experiments, finally we get successful. This is a total device fabricated in this tungsten tips. So we can say this is inside TEM observation. We can see when this is the triggered site process, the current increase largely. Also, meantime, we can from TEM we can see this filament was formed. This enlarged the pictures. But for reset process, you can see the current decrease largely. Also, this filament was also disappeared. I think this is the first time we observe this dynamic process. So here just show a video, but maybe not so clear. Need some maybe several 1 minute. So it's just the begin. You can hear the filament begin to the growth from the bottom to this is the zirconium oxide film. This is the bottom electrode, is the top electrode. The second filament began to growth. So it's a very low area. Because if it's very fast, it's not easy to capture these pictures. So finally, we can observe with the 2 filaments formed in this observed areas. The challenge for this work is just for the how to prepare the sample. This is a big challenge. For also, we capture the reset process. We can reset the first reset just broken from here from platinum top electric field. You can see the second time this gap become larger. The third time is even larger. Then several times the total filament was disappeared. So this is a reset process. This is just prepare a paper and didn't publish it until now. So also do some mapping. We can see really confirm this filament is complex with this is not the copper, is a silver, because we know most the hold of this sorry, for this the inside is still this still is a copper. So this is mapping. This is for silver. Another experiment. So you can see for mapping process is the filament. Also, there's a filament broken. Not so clear, but for my laptop is more clear than the screen. So this is a mechanism we can either for the electron measurement or from the TEM observation can confirm the metal filaments forming and rupture process is responsible for this kind of devices switching on and switching off process. But another problem is we see, well, as we mentioned, there are big variation for this kind of device. The reason is very easy. From this picture, we can see this filament forming process is random process. You cannot control what location this filament is forming, what time is the filament forming. So that's why the parameter is a larger distribution. You cannot fix it. So if you like to fix this the distribution, you should try a way can control the filament forming process. So we just try a very simple way. So if we added some of the nanocrystal in the bottom electrode, we can see what will happen. So here is a nanocrystal. That means there are strong electric field on the tip of this area. That means we just imagine we can enhance the electric field around this area, especially for the tip of this area. Also, we can accelerate in the metal ions the moving speed. That means we can control we imagine we can control the filament forming around this area. So next step, we do some simulation. The simulation results confirmed our the imagination. So next step, we just fabricate the device. Fabricate process is very simple. Just if you can, thinking is very important. This is a very simple way. But thinking this way is not so easy. But this just in the bottom electrode, we just depth the very thin 3 nanometers the copper thin film. After annealing, they are forming this nanocrystal. We can see from the TEM picture, this nanocrystal is around 7 to 8 nanometer. So now, next step, we can see what's the performance of the device. We can see the compare this inserted nanocrystal and the not inserted nanocrystal. We can see this is an inserted nanocrystal. Their set voltage is reduced largely. Also, their distribution is not so large. Here is show different. Also, you can see their parameter is a very narrow, not so large distribution. This way is work. Is really improve the performance of device. But at this moment, you still can see the filament really formed around this nanocrystal. So next, also they demonstrate another performance. Even for the multiple level, you can see the 4 levels for the single cell. Even their cycling is very good. So next, we still use a TEM to observe. We can see this is a nanocrystal. Along this nanocrystal, the filament was formed along this nanocrystal. This is enlarge of this area. So let's prove that this filament really can control to growth around this nanocrystal. To further confirm what consists of this filament, we can do some of the mapping process. Here is a filament. We can analyze the different areas, the elements. We can see for the filament, in this filament area, there are copper, zirconia, also there are the silver. This sample is hosted by the copper ground. So this is the electrode not use a copper, just use a silver. Because if we still use the copper as electrode, we cannot distinguish which comes from the background, this whole background, which from the really filaments. So also do some mapping there. Here clearly see for this filament area, just see the silver, just this filament is very strong. The other area is very dark. For the another material, for the zirconia, this copper is very uniform. So let's confirm this filament is also not only confirm the filament grows around this nanocrystal, also confirm this filament is consists of with the bottom electrode, the same material with. So the third part of the fourth part of for the next generation, the 3D technology. We know this close-path structure is a very the high-density structure than today's CMOS technology. But for this close-path structure, there are one big challenge is there are snake leakage current, because the neighbor cells, the state will influence to another cells. If you like to remove this snake leakage, so you should make some requirement. First, if you use 1R, there are some special requirements. They need this symmetrical array curves. Let me in the opposite direction. They are very large. In the reverse, the negative just can eat this operation. So another choice is to use 1D and 1R structures. We try these 2 ways. One just use this means they are self-rectify effect. We can see we use just choose different material at the bottom, either for the bottom electrode or for the top electrode. We can finally get this very high large rectify device. Just one cell, they either can use to rectify diode-like effect, also can be used for the resistance switch device. This just demonstrates some application use this technology. Also, we try to 1D, 1R structure. This use this material, finish their diode. Their diode have a very large rectifier ratio. They can meet the really application requirements. Also, very high forward current device density. That means can drive these resistors. So this integrates 1D, 1R structures. Also, finally, we just show some of the, if you do the single cell, you just can do some fundamental research. If you really future the industry interested in you for this technology, you finally you should demo some of the integrated circuit. It not need the high density, very large volume, but you should density you really can integrate. So we just the design and fabricate the proposed circuit in the standard foundry. We use 65 nanometer technologies. Then for the RRAM array, we fabricate in our institute. So finally, this is the integrated results. This work also very challenging work. That's because you can see total area is very small because we cannot so much fund to support this research. You have used MPW. MPW finally their cell size is very small, just like the near size. Then we return to our lab. We should still need the further 4 times of lithography. That's a line is a very big challenge. But after even for the coating, resistant coating is not so easy. The small size, how to coating it. So, but finally we solve all this problem, get the hybrid integration, and get the results is very good. So here just my today's presentation, and today's mainstream non-volatile memory face a big challenge for the forward scaling down. So the RRAM is I think is a very strong candidate for the future, the memory application, but there are still a lot of challenges for the RRAM. We just choose this the seamless compatible the high-k material as the active material to do some memory device. Also, the research their switch mechanism, use the inside TM to confirm the or deduce for this switch mechanism. Also, we found a way to control the filament forming process that greatly improve the performance of this kind of device. We also demonstrate some of the integration for this kind of device. There are some potential for future application. So here's the group of our RRAM group. So this is my former student. Now actually he as with the professor, with the scientist now in the Spain, spent 1 year in Spain. This is my 2 posters. He just working here. This is some of the this student just graduated. Then joined another institute. So this also now working in the Lanzhou University. So this young girl, they finished their PhD, now work, they think do research work is so tough, they got to administrative work in our institute. So this just found work in the SMIC, it's a #1 foundry in China. So these 2 is still my students, but this first my student do this RRAM work. Now he started in the Yale University do some research work. He's a very talented student. He actually this year he got the award in the United States. Only 40 students in the United States get this award. So very compatible student. This student also very nice, good student, but he don't like to purchase a PhD degree. So now working in Shanghai. So this is my group focus on the RRAM. So just show some old Beijing and new Beijing. So I finished my presentation.
Sure, if there are questions, Dr. Liu will be try to answer.
Every once in a while, they keep saying that like flash, NAND flash, scaling, first at 28 nanometers, then past 22 to 1, then now you're saying 16 nanometers. So it's been a while, like in the laboratory, these sort of exotic RRAMs, they never sort of come out of the lab, I mean, what do you think the prospects for RRAM, considering the phase change and others still haven't? What's the practical way?
This is a very good question. I think everyone, if you are in this area, you should think in this question. For the PC RAM, have a long history. There are even a lot of reports. They are really commercialized. Actually, maybe last year, the Samsung they announced they are commercialized for the PC RAM. But actually now you cannot find the PC RAM in the market. One of my colleagues from the Samsung, they worked in Samsung for 7 years and now joined our groups. He told me they really fabricated 8 megabits PC RAM. They just use it for their cell phone, because the big challenge is that they are not cost effective. They are still so expensive. So in mainland China, also one group they are focused on the PC RAM fabrication. They even government invests a lot of money for this project. Until now, I think 10亿人民币是多少？1 billion US dollar.
Oh no.
1 billion
$100 million.
10亿是1 billion RMB. 1 billion RMB. RMB is 0.1 billion US dollar, more than this way, for this project. But actually now, until now, I don't think they will success. They even have some what's the standard to finish this project? You can get the market sale for the 5,000 billion Chinese yuan. But I think it's just a joke. Until now, we are also familiar with this group. So that's a big problem. For the PC RAM, the big problem is not so easy for the scaling down, because the mechanism for this you heating from the crystal state to the amorphous state, they transfer. Because they are use a large current to heating let this process transfer. But if you use this large current, it's a big challenge for scaling down. This is one big challenge. Another, their material is so complicated. If you didn't very carefully the fabricated deposited material, the device performance not so good. This is a big problem for the PC RAM. I think for RRAM, for my personal, this is still the research stage for the real application. Honestly speaking, I don't think today it can compete with today's flash memory. Even this project also we get support from Samsung. Samsung gave some money to us for this project. Also, when the venture capital company from the Silicon Valley also collaborate with us. But I don't think, because this company just dedicated for the RRAM. I think it's very fantastic for the Silicon Valley. They just invest, pay money just to do RRAM for this technology. This company just run, I think, the 5 years, but they still demonstrate some similar work like us.
I've got a question. Why do you use copper electrode straight on zirconia oxide again? That's kind of like guarantee you're going to have diffusion. What is the barrier metal between?
That's because for RRAM, there are two kind of different mechanisms. One is based on the metal-based filament forming. This kind of memory, the one pre-requirement is their bottom electrode shows active metal, like a cell. Their basic mechanism is this metal easily to reoxide. Then the migrate into this direct material. Then when go to another electric field, they can reoxide again to the element, from ion to element. So also another different kind of the RRAM is based on the oxygen vacancy. They don't necessarily use this kind of matter for the electrode. But for us, we choose another. This is one reason. Another reason is this kind of the device is easy to conform their maximum for the TEM. If we use the another maximum device like the oxygen vacancy-based device, you cannot use a TM to conform this maximum, because we still interested to conform the maximum.
So for this RRAM, you switch this RRAM many times. The on and off ratio may change.
This is not a big problem. They still very well. Even we can down to 10 to 8 cycle time. The on-off ratio is still very large.
Any other questions?
I'm curious about doing some in-situ working there. Do you consider like an electron beam effect, for example, like a structure?
You mean from the TM? This is a very good question. We also like to confirm what's the electric wave, their influence. But there are some TM experts told us this is the pole is not so large compared to the added the voltage in the device is completely very small.
Like this, if you do long term, like an in-situ calculation, like take about half hours, electron beam reduce heating.
Exactly. Maybe also when exactly. This you get the point, but we also know how to we are not. You have some suggestion how to.
Yeah, I thought something.
Okay, thank you.
Okay, no further questions. Please join me in thanking Dr. Liu for a very excellent presentation on the state of the art in RRAM.
Okay, thank you everyone here.